I'm going to continue focusing on 8.2 area between two curves. This is technically part 2 or a second video for chapter 8 section 2. And in this video I'm going to focus on some types of problems that I've already discussed, whether it be in a video where I went over a homework problem for you guys, or in some other way, maybe in class. I've already discussed these types of problems that I'm going to go over in today's video, but I want you guys to include them in your notes for the record. And the types of problems that I'm talking about are these types of problems. I know we've done a problem where we had to split up the region into two parts. So find the area of the region bounded by the graphs of y equals sine of x and y equals 1/2 x. So we all know that y equals 1/2 x is a line with a slope of 1/2 and a y-intercept of 0. So it does cut straight through the origin. And sine x is this function here. It oscillates, and it's normally symmetrical, but it's just not drawn. It's not the best quality. But if this is the sine function and we have a linear function y equals 1/2 of x, then the area, the region that I'm focusing on is this and this. And we technically have two regions here. So we have region 1 and we have region 2. And to find the area, to answer this question, we're going to have to pretty much find the integral, or integrate from this intersection to the origin, and then integrate the origin to this intersection, and then we're going to add those two answers together. So the first thing we have to do, though, is we have to find the intersection. So go ahead and pause the video and grab your graphing calculator. So I am going to show you how to find the intersection using your graphing calculators. So do that now. So using your graphing calculators, y1 I set equal to 1/2 x, or that's the same as 0.5 x. y2 is sine of x. So the graph, if you have the standard setting, we have way more than what we want. Let's get down to what we want to focus on. So let's go to Windows, and for my x-min, x-max, let's go from negative 2.5 to 0.5. So what I did was I changed my x-min to negative 2.5, my x-max to positive 2.5, y-min to negative 2.5, and the y-max to positive 2.5, just so that I can focus more on the two regions that I want. And there is your graph. Now, some of you guys might already know how to do this. If we go to second trace, we'll go to calculate. And number 5 says intersect. So we're going to calculate the intersection. So what we want to do is, let's say we want to find this intersection here, this most left intersection. You got to move the cursor. Your graphing calculator understands that there can be more than one or more than two functions, more than two graphs, and we can have multiple intersections, just like we do here. We have technically 3. So using your cursor, tell your calculator which intersection you want to focus on. You can only calculate one at a time. So you move your cursor as close as possible as you can to the intersection, not necessarily as close as you can, but just get it relatively close to that intersection. Hit enter. It's going to ask you to guess the second curve, but based on that first curve, it kind of has an idea where your second curve is. So for the majority of the time, it's the second curve is pretty much good. So you just hit enter, and then the third question is going to ask you to guess it. So you can see it's asking you the questions here, and you hit enter, and you see that your intersection is at negative 1.895494, comma, negative 0.9477471. We're going to save this x value for later. So now let's calculate the second intersection. You have to hit second, trace again to get to the calculate. 5. Now we can also do this middle intersection. If you guys don't believe me that that's the origin, 0, 0. If you guys have some doubt, hit enter, second curve, hit enter, guess it, yes, and it should be at the origin 0, 0. But let me go ahead and calculate that last intersection. Second, trace, 5, and I'm going to go as close, not as close as possible, but get a good distance into that intersection. So get pretty close to it, hit enter again, guess it, you're going to hit enter about 3 times. And you see that this one is positive 1.8954943. So we're going to use that to set up the integral. Oh, I just realized that I didn't put region 1 here. So this first region is region 1, the second one is region 2. And thanks to the graphing calculator, we found that the intersections were occurred when x equals negative 1.895494 and when x equals positive 1.895494. Now, look at my setup. Notice that in that first region, region 1 being this one, the top function, the top curve is 1/2 x and the bottom one is sine x. However, in this second region, the second part, we have sine of x is the top function and 1/2 of x is the bottom. So they kind of flip-flop. So it goes, the first integral is 1/2 x minus sine x, and the other integral is sine x minus 1/2 x. And let's use our graphing calculator to calculate this. Remember that you need to hit math number 9 to get to your integral. So set it up. So this is the first one. Hit plus, then math 9 again. So we can add the second part, the second region. And this is the second part. Might look a little messy, but it's all there. It didn't fit in one screen, but it's all there. So here's the plus sign that's attaching the first integral to the second integral. Go ahead and hit enter so we can get the answer. And there it is. Don't forget, truncate 3 places. So you're not going to write the entire thing as your answer. You're going to truncate 3 places. And remember that if you do not want to truncate, so that's your answer truncated, you can always round 3 places. The key is 3 decimal places. So you're either truncating or rounding 3 places. Okay, here's another example. Suppose we have the curves x equals y squared and y equals x minus 2. I know I've done these types of problems also. So notice that if we integrate this in terms of x, or with respect to x, we have, first things first, we're going to have to change this to y equals. So we now have y equals plus or minus radical x. We're going to have to deal with y equals plus x and y equals minus, and radical x, not plus x is plus radical x, and y equals negative radical x. So, and then we have to divide this into regions. Okay, you didn't have to do all this. I just really wanted to show you how it can be a bit of a hassle. We have to break it up into two different regions. Deal with y equals positive radical x and y equals negative radical x. Let's think of an alternative way to deal with this. This I do want you to write. So if we were using, remember that Riemann sum consists of an infinite amount of rectangles. If we're using vertical rectangles, then we are going to have to split the region into two parts. We don't want to do that. So if you were able to make the relation to one of the videos that we already did, and you were realizing that we are going to integrate this in terms of y, that is correct. So we are going to integrate this in terms of y. So we are going to change this to x equals y plus 2. So we have x equals y plus 2. We have x equals y squared. Before we move on with this, go ahead and find the intersections. Remember that to find the intersections, you have to set the two equations equal to each other and solve. So you set x equals y plus 2 equal to x equals y squared and solve. Go ahead and pause the video and do that now. And if you set up the quadratic function in standard form, factored and solved, you would have gone y equals 2 and y equals negative 1. So that tells us that this intersection occurs when y equals 2. This intersection occurs when y equals negative 1. Okay, so go ahead and take a break from taking notes just for right now. You don't need to copy this, but what I want you to do is I want you to see the relationship that I'm trying to make with one of the problems that I did in a video. This is just like that one problem in the video where I had you guys reflect across the line y equals x, because inverse functions reflect across the line y equals x. And if we were to reflect this, we would have this function. So the graph that we originally have is this, and we reflect it across the line y equals x, and we now have this function. Okay? So I'm going to show you guys an easier way of doing this without having to do the reflection. So when using horizontal rectangles, in other words, when we integrate with respect to y, just like we're about to do so for this problem, the area is the integral with the limits of the bottom curve being the bottom endpoint, the top limit, I said curve, but I meant the lower limit being the bottom endpoint, the upper limit being the top endpoint, and it's the right curve minus the left curve, and it is dy. Okay, so it's the right minus the left. So here is the top, here is the bottom. Those are going to be the limits. The right function is this one here, the line, and the left function is this one, what is x equals y plus 2. I'm sorry, my right function is y plus 2. My left function is y squared. So this is your setup, the integral from negative 1 to 2 of y plus 2 minus y squared. Go ahead and use your graphing calculators to complete this, and I'll show you the answer in a bit. And this time I decided to show the answer in the F and INT form. Those students who don't have an updated calculator would have to put the function first. Notice that I changed from y to x, comma, with respect to x now, comma, lower limit, comma, upper limit, and you get your answer. That's all I wanted to do in this video. That's it.